Howdy crew! In this lesson, we're going to take a look at finding maxima, minima, and critical points for certain graphs. You've been doing graphing literally since Algebra 1, and our job here is to identify certain features of functions and how to find them using calculus. So in this lesson, we're going to take a look at what did curve sketching look like during your pre-calc course, and even before that, defining what a minimum, a maximum, and a critical point actually are. We're going to take a quick look at what it means for a function to be differentiable as well, what that means and what it looks like, and trying to figure out what a critical point is and how to find it. So I set up a chart for you outlining more or less what you did in pre-calc. If I asked you to graph the function of this quadratic, 3x squared minus 3x minus 6, one of your first jobs is likely to find the y-intercept. In this case, you just plug in x equals 0. Everywhere you see an x, put in a 0. You get negative 6, plot the point. Find your x-intercepts. You would take this equation, set it equal to 0, solve it, and try to find where the graph hit the x-axis. In this case, x equals negative 1 and x equals 2. You can plot those points. And you knew the end behavior. You took a look up here, and you saw that if you were finding the leading coefficient was positive, so your ends would have to point upwards. And we look at the degree, knowing that the degree is even. In this case, we have a degree 2 polynomial. The end behavior had the same direction. So we knew that since it was positive, the ends would be going up, and they both be heading the same direction. And once you did all of that process, you would have connected the dots. Now the question is, how do we know if there's points that are helpful that don't fall into either one of these categories? And when I say helpful, I mean, for example, this vertex point. There's certainly a way without calculus, using a formula like x equals negative b over 2a. For a quadratic, you'd be able to find it pretty quickly. However, that's not a guarantee when it's an x to the third power, for example. So how would you find points like that? I have some definitions for you. Here's a nasty definition for what is meant by an absolute maximum and an absolute minimum. What I want to focus your attention on is this statement right here. Is if you had some number c inside some interval, and no matter what happened, the value when you evaluate the function at c, it turned out to be greater than or equal to everything else, that has to be a maximum. An absolute maximum is just a point that's taller than those around it. That y value happens to be bigger than everything around it. A minimum is exactly the opposite. For any value c, every other value is above it. So an absolute maximum is a point taller than those around it, and a minimum is a point shorter than those around it. Nothing different from Algebra 1, just throwing some symbols at you. Now the question becomes, where can maxima and minima, this is the singular version of those two words, where can maxima and minima occur on a graph? So if I take a look, for example, at this graph in the middle, it's pretty clear that this spot here at the top, that's going to be a maximum. We can call that a max, for sure. And we're going to assume that this graph will continue forever in both directions. This one would not have a minimum. This graph over here, which appears to be a cosine function of some kind, there appears to be several minimums and at least one maximum. There's a max there at the top, a couple minimums here at the bottom. Similar sort of thing happens here, where it's different points we've got some minimums and maximums. This spot here at the very top, at what we call a cusp point or a sharp edge, we call that a cusp. This sharp corner, something different happens there. Certainly a maximum, because it's taller than any other point around it, but something interesting is going to happen here. In this first example, there really is no minimum or maximum. There's no one spot that's taller than the rest. So this one wouldn't have any. The question becomes, where do those maximums and those minimums occur? And it happens when the graph happens to go flat. You notice that all these maximum spots and all these minimum spots, the graph is horizontal. And in that case, when we know that a graph is flat or horizontal, the slope of the tangent line at that spot happens to be 0. The only exception to that rule is this cusp point. At the cusp point, we're going to see that something different is going to happen. But generally speaking, maximums and minimums occur when the graph goes horizontal, when the slope of the tangent line turns out to be 0. So here's our definition of a critical point. If C is an interior point on the domain, meaning C is somewhere in the domain, we call C a critical number if the derivative at that point is 0. If the derivative at that point is 0, that is a critical spot. Or if the derivative is undefined for some reason. So for example, if it turns out to be a fraction with 0 in the denominator, or something else funky goes on, causing the derivative to be undefined at that spot, it would also be a critical number. Now a critical point is two numbers. Remember that a point has an x and a y. So a quick question here is, how can a derivative be undefined? How is that possible? So in our case here, the word differentiable. Differentiable means that you can find the derivative at a given spot. Sometimes you can, sometimes you can't. There are two spots on these two graphs. There are two spots where you cannot find the derivative. And those two spots are the sharp corners, these cusp points. And here's why. If we consider the tangent line, as we approach 2 from both directions, from the left and from the right, I think you'd agree with me that the slope of the tangent line on the left side definitely has to be a positive number. So as x approaches 2 from the left, that number has to be a positive number because we're going uphill. But as x approaches 2 from the positive direction from this side, our slope is negative. It's going downhill. So how is it possible when we get to this one spot, how is it possible that they're going to match up? It isn't. Same thing is true over here. So at that exact corner spot, the derivative cannot be found. So we call those points spots where the graph is not differentiable. So what's our process going to be? How are we going to find critical points? Our job here is going to be to find the derivative of that function. And we're going to determine where the derivative equals 0 and where it is undefined if there are any spots where that happens. Now, if we're in a specific situation where we're only looking at the part of a function, a specific domain, say from 0 to 4, we're also going to evaluate the endpoints because it is possible that the graph starts higher than it will ever get. Then once we found our critical points, we're going to find the y values for every x value that we do find. So here's an example. Find the absolute extrema of these two. When I say extrema, that's the more general term of minimums and maximums. All right, let's go. First step, got to find the derivative of the function. So here it's just a straight power rule question. Bring that exponent down and multiply times the coefficient. So 3 times 1/3 is 1. X, and we'll reduce that power by 1. Same thing here. -5/2 times 2 is -5. And reduce that power by 1, so x to the first. And the derivative of 4x is 4. Now we just said that we're going to set that derivative equal to 0. Our goal here is to try to find every spot where the slope of the tangent line is 0. Or in other words, that graph goes horizontal. I'm guessing it's pretty obvious to you that we're going to factor that. I see two numbers that multiply together get 4, add together get -5. It's going to be -1 and -4. Set both of those factors equal to 0 and solve. Now we also want to take a look here as well. Are there any spots in this derivative, this x squared minus 5x plus 4, are there any spots where the derivative is going to be undefined? And the answer is no. This is just a quadratic. It's defined everywhere on its domain, so there's not going to be any domain issues. We do need to find the y values here, though. And to do that, we're just going to make sure that we plug in those numbers. So everywhere we see an x, we'll plug in the 1 back into the original function now, because I want to see where the original function was. And we're going to plug in a 4 as well. And when I do that, I get values of 11 over 6 and negative 8 over 3, respectively. If you weren't convinced by what we just did, you could take a look at its graph as well. We can see there's a maximum here at this spot and a minimum at this spot. A little bit short of 2 on the y-axis and a little more than negative 2 on the y-axis at our spots of x equals 1 and x equals 4. So some conclusions we can make here. At a critical point, there's 3 possibilities. The graph has either gone flat, meaning the derivative is equal to 0, so the slope of our tangent line is 0. The graph has gone vertical, as in the derivative is undefined. Or that graph has a cusp, a sharp edge. You can't find the derivative of a graph when it has that sharp edge. When you're finding the critical points, you're going to find the derivative, find where it's equal to 0, and solve. And the same is going to be true where the derivative is undefined. How do you know if a point is a maximum or a minimum? That is a more challenging question. We're going to find that out in the next series of lessons, how we can actually work through whether a point is a minimum or a maximum using calculus. Nice job.